Section 8.1 is on page 584. Talks about arc length. Suppose I'd like to find the length of a curve. And let's say the curve looks something like this. If I take this from A to B. Now the problem with this, it's not a straight path. This is a curve. So what I do, I break this into n pieces. And what I do, I put straight lines. And what I'm going to do, I'm going to approximate the straight lines to see if that works. So if I take one of those right here, for example, and I blow that out of proportion, the curve looks like this. And the line that I picked will happen to be straight. So if I call this line S, this is delta x and this is delta y. And assume this is S sub 1, this is S sub 2, this is S sub 3, and the list goes on, the tradition. Now keep in mind this is an arc, and that's why I'm using S. We know from trig S equal R times theta, but we're not going to go there. We're going to approach this a different way. This is reserved for a different section. For now, I'm going to look at this, say, all right, well, if I use my Pythagorean, so let's say I pick this to be the ith, not necessarily the first, right? So that is, I could go 1, 2, 3, 4. So if I want to figure out delta S sub I squared, that would be delta sub x squared plus delta y sub I squared. Now, if I take this and I approach this two different ways, if I was to divide everything by dx, that would equal 1 plus dy di squared over dx sub I squared. And I could say ds sub I over dx sub I squared equals 1 plus dy sub I over dx sub I quantity squared. And from there I could say, well, this would mean that ds sub I dx sub I equals 1 plus dx, dy sub I dx sub I squared under a radical, and that would mean that ds sub I equal the square root of 1 plus dy sub I squared, d sub y sub I, d sub x sub I squared, delta x sub I. If I multiply both sides by the LCD, there it is. Now keep in mind, I could have approached this differently. I could have said, you know what, why would you divide by delta sub x? I want to divide by delta sub y. I couldn't have said d sub x, d sub s sub I divided by, so if I divide each of those by d sub yi squared, that will be d sub x sub I squared. And if I follow the same trend as what I did, I could get d sub s sub I to equal the square root of 1 plus d sub x sub I squared over d sub y sub I squared plus 1 delta y sub I. You know what, I could fill in the blanks. It's only a couple of steps. So this is d sub s sub I, d sub y sub I squared equaling the square root of d sub x sub I, d sub y sub I squared plus 1. And if I cross multiply, I pretty much get this result. Now, I do know from before, the same idea applies. I could say, you know what, this, a small correction I needed to make. I'm sorry. This is S sub I, and this is D sub S sub I. That was my mistake. So when I was looking at those, I was really trying to figure out what I really wanted. I wanted to find the actual S sub 1, the actual S sub 2, the actual S sub 3, and so on and so forth. So if I look at what S is going to equal, I'm going to say that's roughly delta S sub 1 plus delta S sub 2 plus delta S sub 3, and the list goes on all the way to delta S sub n. Assuming this is the last one, this is the first one, that right there, S sub 1, S sub 2, and so on and so forth. So I could say S is roughly the series I equal 1 to n of ds sub I. And if I wanted to know what S equals, I will take the limit as n approaches infinity, taking the partition to be approaching 0 or n approaching infinity, same idea. And what that comes out to be the integral from a to b of ds, where ds is either the square root of 1 plus dy dx squared dx, or the square root of dx dy squared plus 1 dy. And from this, we really arrive at the following theorem. Now, this derivation is needed in chapter 10, and then we're going to tackle that back when we get to 5c. It's a big deal to understand that idea, since you're going to take that and apply it on a lot of applications. So keep in mind, this is nothing more than the integral from a to b of ds. Alright, where ds is either this piece or this piece, and it's good to keep that in mind. We're going to do this slightly different than the way the author wants us to do this. We're going to work with this from the derivative point of view. Which of those should you use when you do a problem? Well, it's up to you. I'm going to show you a nice way of really dealing with those, and this should run smoothly. So, I'm going to start looking at the first problem, and this is problem set up an integral that represents the length of the curve. So we're going to set up all of those actually. It says then use a calculator. We're not going to worry about that. That's if you have a graphing calculator. We don't. So on page 589, the way it works, I'm going to start by reading the problem, and it says find the length of the curve. Well, the length of the curve is the integral of ds. ds, would that be in the x direction or the y direction? This is how we're going to set this up on every problem. We're going to ignore the directions of how they do things in the book. Instead, we're going to look at, you know what? I see this is defined in terms of x, meaning if I write this as a dx, x will run from 0 to 2, and that would mean it's the square root of 1 plus, and automatically, what's the derivative of that? Wouldn't that be the product rule? So wouldn't that be e to the negative x minus x e to the negative x? And there it is. Now, theoretically, you could set up every problem a dx or a dy. So there's no set way of doing that, and they can't force me to do this one way or the other. That is, if they ask me to do a problem, I would choose based on two things. One, the derivative, and secondly, the limitation on x. Right? Now, also, The only time I might reconsider doing this in terms of x, if I can't integrate, I look at the integral and it seems to be very challenging, then I would switch the order. I'd like to look at another problem. And the following problem, theoretically I could do every problem both ways. Oh boy. Okay. And if I look at number 6, again, I could complete the square on the y if I really want. And I could solve that for x if I really want to. Highly not recommended. Right? And then say, okay, well, if I put 0 in there, what do I get? If I put 2 in there, what do I get? And so on and so forth. So something that I could do if I want, but that's not the way to go. The way to go is for you to say, you know what? I have two formulas. That is, I could say this is the integral of the square root of either a dx there or a dy there. But in this case, what do you notice? In this case, if I am to plug in a derivative of this, then y is right there. So it helps me to start with a dy. There's no way of forcing you to do dx or dy. That will make it 0 to 2 automatically because that's already set up that way. And all what I need is the derivative with respect to y. That will be 2y minus 2, and there it is. By the way, there's an exception. There are a few things about this. I'll be talking about that in other sections, not in this section. For now, we just want to tackle this and get it out of the way. The next problem I'd like to look at is number 14. And on 14, I'll look at this, say, all right, well, find the length of the curve L equal the integral of ds. And that is the integral. In this case, I notice I could take a derivative with ease with respect to x. So again, this is my choice. Do I go for dx or dy? It's up to you. In this case, I suggest you go for dx since everything's set up in terms of x. And that will be the derivative. What's the derivative of this? Derivative of natural log is 1 over the argument times the derivative of cosine, which is negative the sine of x. So this is actually the integral from 0 to pi over 3 of the square root of 1 plus tan squared of x dx. That is the integral 0 to pi over 3 of, this is secant squared, so this is secant of x dx. And we agreed that you're going to memorize 3 integrals for me. One of them is this. Right? And that would be natural log of secant of pi over 3 plus tangent of pi over 3 minus secant of 0 plus tan of 0. And that turns out to be natural log of two over 1 plus radical 3 minus, this is 1 minus 0. And on my test, that's all you need. Once you plug the values in, you really don't have to simplify that. That's fine. And I want to see if I could start another problem really quick. And I'd like to look at number 12. And here again, I'm looking for the arc length. That's L equal the integral of ds. In this case, that would be the integral of the square root. And I notice here, everything's set in terms of y. That would be y equal 1 to y equal 2. That means that's a delta y of 1 plus the derivative of this. To bring the power down, that will be y cubed over 2. This is 1/4 y to the negative 2. Bring the power down, subtract 1 from the power. And if I look at this really quick, I'll notice this is the integral from 1 to 2 of the square root of 1 plus, and this will be y to the 6 over 4 minus twice the product of those. When you take 2 times the product of those, you'll get 1/2. They cancel out, plus 1 over 4y to the 6 dy. That will be the integral from 1 to 2 of the square root. And notice what happens. If I combine those, I will get a positive 1/2, and that is y to the 6 over 4 plus 1 over 4y to the 6. And something I want you to pay attention to, we took this squared, we got this, and now we have this. The only difference between those is the plus to a minus. So this is a new integral that didn't come up yet. If this match this, and the only difference between those is a plus or minus, then doesn't that mean that this is actually y cubed over 2 plus 1/2 y to the negative 3 squared dy? And from there you could finish the problem, because I think I'm out of time. And there's the homework.